Hi again. In this episode today, I'm going to talk a little bit about the history of statistics, and I promise it will be brief. I'm going to talk about the two major categories of stats that we cover in this class, and I'm going to close with some hopefully good news about how visual statistics can be. That's great news because we're all visual learners. We all have a brain, hopefully a little bit bigger than this little guy here, with a great deal of cortex devoted to vision. Okay, so lots of people like to say that, oh, I'm a visual learner, and well, if you're a human being, you're a visual learner. Okay, so here we go on the history. Now, I really hesitate to talk too much about these two topics which are so popular with students, history and statistics, together at the same time. So I promise this will be brief. The word statistics does come from an Italian word, statistica, which refers to people that dealt with affairs of the state. Now, in one of the great affairs of most states is to keep track of people for the purposes of taxing them. So that's kind of our origins here. So now I'm going to talk about some of the pieces that contributed to this discipline. Now, this is certainly not an exhaustive history, nor would you want it to be. These are just some of the topics from the background that kind of caught my attention, caught my interest. So, I'm happy to say that statistics has been contributed to quite a bit by psychologists. Early psychology, with its emphasis on personality, and you think of people like Sigmund Freud and discussions of personality. Now, while he wasn't much of a scientist nor a contributor to statistics, other psychologists from those days certainly were. Okay, and also people like Francis Galton was a major contributor to statistics. I like astronomy, so there's two things I like about the fact that astronomy has contributed to statistics. One, I've always liked astronomy myself. Secondly, astronomy is something of an offshoot of physics, and I love to tease physics for the fact that a lot of physicists tend to look down their noses at the rest of sciences and really look down their noses at us in psychology, saying that it's hogwash that psychology is a science. They don't think anyone but themselves are scientists. And so I like that astronomy, being something of an offshoot of physics, suddenly found itself in a desperate need for statistics when they came across celestial bodies that didn't behave as their mathematical expressions had predicted. Okay, they would come up with very precise mathematics, as you probably know, to describe the movement of stars and planets and the locations. And when they would look in their telescopes to see and confirm that something was where their mathematics predicted it would be, lo and behold, they would find it's not quite there. It's a little bit off. And so they would scramble back to their mathematics and revisit what they might have done wrong and revise them perhaps a little bit, and then come back to their telescopes and look to confirm their predictions and see, oh, they're off. And they went back and forth. And finally they realized there's nothing wrong with the telescopes. There was something wrong with there wasn't really anything wrong with the mathematics either. What was wrong was the universe. The universe contains something of a bit of chaos. Now, no less of a scientist than Albert Einstein, earlier in his career, had a very famous saying that he refused to believe this. Physics is all about, it's a reductionistic science. You reduce things to their elemental properties and reduce those down to mathematical properties, and you should be able to come up with a deterministic answer to anything if you find the precise enough initial values of something. And he refused to believe that there could be chaos. And his famous thing he said was, I refuse to believe that God plays dice with the universe. Well, he later, by the time before he died, he recanted that and acknowledged that, yes, the universe contains chaos, and chaos is quite interesting and beautiful in its own regard. Well, what is chaos? Well, certainly you can recognize that chaos exists in human behavior. People are not predictable. People, even in very predictable circumstances, people sometimes are very unpredictable. Well, so it's not surprising that people are chaotic and that we need statistics and probability to understand them better. But how about something simple like boiling water? Okay? Pure water at sea level temperature should be very, very predictable. Indeed, if you know the temperature, you should be able to predict with almost perfect precision where individual components, say molecules, might be in that pot of water as it's heating. But if you've never noticed this before, next time you're boiling tea, look down at your pot of water. As it's slowly heating, the temperature is consistently rising if you have a decent oven, a stove, and so that is a very deterministic system. The gradual increase of heat is a very consistent deterministic system in a pure pot of water, and something called convection starts to happen, and the hot water at the base starts to rise to the top because heat rises, and the cooler water then settles down to the bottom to get heated, and you start to get a rolling pattern of convection. And if you look down at the pot of water, you can see these cells of convection starting to roll, and as the water increases even more and more in temperature, it starts to go faster and faster. And then almost all of a sudden, like flipping a switch, it descends into chaos and it starts to bubble and boil, and it no longer looks like convection, and you can no longer reliably predict where molecules of water are going to go. Okay, so nothing has changed as far as the determinism of the system. The water temperature, the heat did not suddenly change, it just gradually rose, but it reaches a critical point, the boiling point, and it turns into something chaotic. And then you need statistics, or a different set of mathematics at least, to understand and predict where things are going to go. Okay? I could give you other examples. So astronomy was head on with this idea that the universe does seem to have somebody playing dice with it, and they needed statistics to understand it better, so they begin to have to develop them. All right, so there we go. All right, I have a biology minor, and I like to be able to use it whenever I can. So studying correlations in biology, things like population dynamics and so on, and of course genetics is very strongly associated with probability. What's the probability? You've all had this kind of genetics in your biology classes, you know. If you have a brown-eyed mother and a blue-eyed mother, what's the probability that any given offspring will have brown or blue eyes, and so on. Okay, so probability is certainly associated, and therefore statistics certainly associated and used in biology. I'm not particularly interested in life insurance, but I'm throwing it in there because life insurance, beginning back in the 17th century at least, had a need for better predicting mortality. So there we go. That's all I'm going to say about that. Related to that, back on a much more colorful note, I like the fact that shipwrecks and piracy has had an influence on studying and understanding statistics related to the life insurance. People wanted to insure their ships and the people on them, and pirates would come in and mess all that up, and therefore they needed ways to figure out the odds of things like shipwrecks and piracy. So pirates have an influence on our discipline of statistics. Okay, this one surprises many people, but farming and agriculture has had a major influence on statistics. You're going to be learning something called the analysis of variance, which is often called the F test at the end of this term. And the F test is named after Roland Fisher. Fisher was an agronomist and gave us one of this major category of statistics that we use in psychology, the analysis of variance. Studying probability for gambling, you can certainly understand how gambling is all about probability, and people who wanted to gamble and people who could afford to gamble could also afford to hire people to understand and determine the probabilities of their winning certain games and whatnot. So people, like kings and so on, would hire people to investigate the probability for them. So gambling has contributed to the discipline of statistics. My favorite example of all, though, comes from this one, from brewmasters. There was a brewmaster at the world-famous Guinness brewery in Dublin, Ireland, named William Gossett. He had degrees in mathematics and chemistry and was hired by this already successful company to build better beer. And being very scientific minded, he approached it as a scientist might. If you want to brew a better beer, you can do it haphazardly, or you can try to do it very scientifically. Now, Gossett had this mathematics and scientific kind of training, so he approached it in that way, in trying to understand better how to use the yeast that's in beer. He varied amounts of it and how long things would brew and details like that. And he realized that he didn't have a way to analyze what he was collecting. He ran into a wall. There wasn't statistical methods out there to help answer the data that he was collecting, understand it. So he developed it himself. Now, the owners of Guinness were very nervous about having trade secrets revealed. Now, they knew that they hired a scientific person. They had a history of hiring people like this, and they had somebody previously that had revealed some trade secrets, and so they didn't want that to happen again. So they had a policy forbidding their employees from publishing in scientific journals altogether. Now, Gossett knew was onto something, and so he began to publish and do his work at home outside of business hours, and published under a pseudonym. His pseudonym was Student. So there are many publications back from those days by this mysterious person named Student. And there's interesting stories about this and other famous statisticians in this wonderful book, The Lady Tasting Tea. So my book of the day today is this. If you're at all interested in statistics and its sometimes colorful history, lots of good stories in this. Okay, so there's good stories about William Gossett and how he circumvented the policies at his employers and went on to publish something very famous that we're going to learn and use in this class, something called the t-test. Used to be called Student's t-test, and more recently we just go by T. T, the letter T, not the T as in lady tasting tea. The t-test. We'll see that very, very soon. Okay? So, when I think of t-tests, I'm in the back of my mind somewhere thinking about Guinness. And when I'm drinking Guinness, well, I raise my glass and give a toast to William Gossett, the contributor to the t-test. So there we are. There's my brief, hopefully colorful background of statistics. So let's go on. Let's talk a little bit about what statistics are for. Okay? There are two major types of statistics and purposes that we're going to be covering in this course. And the first is descriptive. Now, descriptive statistics are just what they sound like. Their purpose is to summarize and describe the data. So just as descriptive research, which we talked about earlier, is often a first step in a scientific investigation, descriptive stats are the first step in understanding your data. These are things like means, medians, and modes, and some others that we'll cover in, of course, some detail very, very soon. So descriptive statistics. The second category are the inferential statistics. These are admittedly a little bit more thick, a little bit harder to understand for many, and so we'll cover those after we get a handle on the descriptive. Now, inferential statistics are to help us make predictions from the known to the unknown. So when we collect data, we have a sample of data. We have a sample that we know something about, and we don't usually set out to do research to understand that sample. That's not our goal. We're using that sample as a tool to understand a larger population that we don't have access to. So when we make predictions about the unknown population from what we know about a sample, we turn to inferential statistics. As I've been saying, human behavior is not very deterministic all the time. We have to rely on probability. So the backbone of inferential statistics is that probability. So we try to determine what is the probability that the population will act this way. For example, when we do an experiment, what is the probability that the population will behave similar to the way that the participants who got the treatment in my experiment behaved? Okay, we turn to inferential statistics like Mr. Gossett's t-test and Mr. Fisher's f-test. Those are two classic inferential statistics that we'll cover this semester that do just that. They help us understand the probability that something occurred due to something real, the treatment that we gave, as opposed to chance, all the chance factors that go into behavior. We try to tease them apart with inferential statistics. Okay, so those are the two categories that we're going to be covering. We will return to those shortly. Before we jump into those descriptive statistics, we're going to talk a little bit about research methods. You can't very well make much sense of statistics before you can understand research methods. And we had a tough decision to make about these courses, whether you should take research methods and then stats, or whether you should take stats and then methods, or should we lump them all together somehow. Well, we decided that it was probably easier to give a brief enough introduction to methods so that the stats would make sense than to try to start with the methods but giving a brief enough introduction to statistics to help the methods make more sense. So we decided to do it this way. So we will spend a little bit of time in upcoming videos talking about some research methods. Okay. So one thing I want to close on today is a reassuring note, I hope, that statistics can be and is a very visual enterprise. And I do approach it, and I do try to teach it in a very visual way. Like I said earlier, we're all visual learners. So for example, one of the concepts that we'll be talking about a lot this semester, because of people like Gossett and his t-test and Fisher and his f-test, we'll be talking about so-called distributions. Okay, the distribution, a distribution is a depiction of how frequently something occurs in a population, how frequent scores occur, how frequent various IQs are in the general population, how frequent shoe sizes are distributed in the population. Okay, it's frequency distribution, sometimes called distributions for short. The one that we're going to talk about until we're red in the face this semester are so-called normal distributions, or bell-shaped curves. And we call them bell-shaped curves for fairly obvious reasons here, because they are bell-shaped. Okay, so normal distributions occur all around us. Okay, now this isn't a very detailed, this isn't a labeled graph by any means, but along the bottom of a distribution we have the individual scores. So if we look at intelligence, IQ scores for example, at the low end we have low IQs here on this side, on the left side of this curve, and in the middle we have medium intelligence levels, and at the right we have high genius level intelligence. The height of the graph tells you how frequent it is. So thankfully, relatively few people are down here in this very low end. These are the Forrest Gumps out there, I suppose. Most of us are here somewhere in the center, okay, with a vast majority of people are here in the middle on intelligence. And at this very upper end here are the Einsteins, the Stephen Hawking's, and the Gossets and the Fishers and the Metcalfs and who? Those people are up here. There's relatively few geniuses out here in the world. Okay, so anyway, there's an example of something that's distributed on a normal distribution. As we'll see, much of what we study in psychology is normally distributed. Okay, I like this clever little way to describe what a normal curve is by putting it in the shape of a normal curve. The normal law of error stands out in the experience of mankind as one of the broadest generalizations of natural philosophy. It serves as the guiding instrument in researches in the physical and social sciences and in medicine, agriculture, and engineering. It is an indispensable tool for the analysis and interpretation of the basic data obtained by observation and experiment. Okay, we see them all around us. Okay, now we don't see too many of these anymore. What do you call these things? Not a sundial, not a sanddial. The name is escaping my I can't believe I can't think of it right now. A sand clock, right? Hourglass, an hourglass. Duh. I'm going to try that again. We see normal distributions all around us in the world. Now, we don't see too many of these anymore. Hourglasses being used to tell us what time it is. But if we look closely at the sand falling in an hourglass, we see that it's forming something of a three-dimensional normal distribution. In more everyday kind of real life, if you look at ant hills and termite mounds, okay, the ants are throwing the dirt out of their hole and they throw it in something of another three-dimensional sort of normal curve. Most of the sand they throw out lands very near the hole, and every so often they whip one out pretty far and it falls very far away. Okay, the further away it is, the less likely it is to fall out there, and we wind up with a three-dimensional normal distribution. The sports world is full of normal distributions. These maybe are a little bit harder to see, and maybe you have to turn your head sideways to see them, okay? So at the front end of this race, we have a relatively few number of cars that are super quick. Most cars are in the middle here, and a few laggards trailing off in the back. Likewise in a bicycle race. I'm recording this the day before a Super Bowl. I can predict that tomorrow, when there's a win, after somebody wins the game, some very eager fans are going to rush the field. Okay, if you imagine people rushing a field, a few people are going to decide that that's a good idea and that they want to do that, and they're going to start. Okay, a relatively small number of people trickle out onto the field, and then more people decide they want to join them, and you have a big mass of people, and then pretty soon it trickles down until the last few people decide to go out there. You have another kind of three-dimensional sideways normal distribution. I want to close with my very favorite example. I just noticed this the other day. I was popping popcorn. Now I was popping it in my microwave, not in this good old-fashioned Jiffy Pop. Do any of you remember Jiffy Pop? Buying this and shaking it on the stove? Did you do that? I don't know if it's still around even anymore. These days everybody microwaves popcorn. I was doing it too, and I was standing there waiting for the popcorn to come out and listening to it. Then a few kernels start to pop, and then a few more, and a few start out popping, and then more and more, and pretty soon most of them are popping, and then it starts to slow down and trickle down to a stop again. Okay, another auditory normal distribution, the speed at which popcorn pops. Okay, so the normal distribution is all around us, my friends. Now I want to close with an assignment here. I want you to go and watch a video with my hero, Hans Rosling. Hans Rosling here, standing in the pool of water, he's a Swedish researcher of public health. He's not a statistician, but he has a absolutely wonderful website called gapminder.com that I have a link to on the course page, and a link here to this video. So this is your assignment, to go watch The Joy of Stats. It's an hour long, and I promise you, you will enjoy it. Hans Rosling is an amazing teacher, and he will convince you that Statistics is indeed the sexiest subject around. So go watch this video and tell me what you think of it. I promise, promise, promise you will find it fascinating. Enjoy it. And I'll see you soon. Thanks. Bye-bye.